Okay, Chemistry 3101. Where we left off was right here. We finished section 8.8. We were just getting ready to start section 8.9, which deals with catalytic hydrogenation. But before we get into this in detail, I want to show you, if you go all the way to the end, okay, of the chapter, when it has the review of all the reactions that we've covered. So if you start at reaction number 1 on here, we covered that. That's hydrohalogenation, which occurs with Markovnikov regioselectivity. And the reason I put the little blue star here is because I expect you to know the mechanism for that reaction. The next one is an anti-Markovnikov. So the first one was Markovnikov addition. This one is anti-Markovnikov, and that is affected using HBr in an organic peroxide. So that's that ROOR. That's the organic peroxide that is required for anti-Markovnikov addition. You don't have to know that mechanism. It is covered in the class, but not until chapter 10, so don't worry about it now. The next one is just a catalytic hydration. So, acid catalyzed hydration, and that proceeds in a Markovnikov regioselectivity. And then we talked about oxymercuration, demercuration, which also proceeds with Markovnikov regioselectivity, but it avoids carbocation rearrangement. So if we need to prevent a carbocation rearrangement from occurring, we would use oxymercuration, demercuration. Otherwise, we stay away from it because it uses mercury. Again, the Markovnikov addition of water across a double bond, I expect you to know that mechanism. The next one is hydroboration oxidation. This proceeds with anti-Markovnikov regioselectivity. The mechanism is covered in detail in the textbook. However, you don't need to know that mechanism. Okay, so where we're going to start today is here. This is going to be section 8.9, which deals with catalytic hydrogenation. So we're going to cover that in detail. Then after that, we're going to take a look at this reaction. This is called bromination or halogenation because the same reaction can be done with chlorine, but we usually use bromine for the reaction. So we'll get into that in detail. Then we're going to talk about what's called a halohydrin. So this, when we have a halogen and then you have a hydroxyl group on the neighboring carbon, that's called a halohydrin. So we'll talk about halohydrin formation, and we'll talk about the stereo selectivity and the regioselectivity of that. Then we're going to get, you see that you have two hydroxyls next to each other here and here. What's the difference? In this one, they're cis to each other, and in this one, they're trans to each other. So we're going to talk about forming cis diol. So this is called a diol, right? Because it's got two alcohols. And we're going to talk about forming trans diols, and we're going to go into quite a bit of detail on both of those. However, the only mechanism you're required to know here would be the second step for the formation of a trans diol. Then the last reaction that we look at is this one here, and this is called ozonolysis. And you probably recognize this little character here, O3. That's ozone. You've all heard of the ozone layer, and maybe some of you have rented an ozonizer. I did years ago. Anyhow, so that's what we're going to cover today. Today we're going to take a look at all of these reactions, okay? And then when we get to the end of the chapter, we're going to combine the entire thing, okay? We're going to put everything together, and we're going to mix it with chapter 7, and we're going to start looking at making some interesting molecules. So that's what we have in store today. So let me go back here to my hydrogenation section, which was all the way up. Come on, Mr. Dion. It was right here. So catalytic hydrogenation. And if you looked at the slides before coming to class today, you'll notice there's a bunch of sections of the hydrogenation portion that we skip, and I'll be very clear about which portions you don't have to be aware of. So what is hydrogenation? Some of you have probably heard of things like partially hydrogenated vegetable oil. That's where margarine comes from, for example. That's where trans fats come from because they're not natural. They come from the hydrogenation of plant fats, essentially. But hydrogenation, what it is it's the addition of H2 or hydrogen gas, right? Because you know H2 is a gas. It's the addition of H2 gas across a carbon-carbon double bond, and it requires a metal catalyst. There are actually 3 metal catalysts that we accept in Chemistry 3101. It can be palladium, platinum, or nickel. You have to memorize those, palladium, platinum, or nickel. And this is not a joke. We really don't discriminate between these. And so if you wanted to convert this alkene, so this would be what? 2-methyl-2-butene. If you wanted to convert that to 2-methyl-2-butane, you would use hydrogen, right? Hydrogen gas, and you could use platinum as your metal. If somebody else put, let's say somebody else had written nickel or palladium, that would be perfectly acceptable. And you can see that this reaction works really well because we get a 100% yield. Okay, so a high yielding reaction. However, one thing that I would say about the hydrogenation reaction is you do have to be cautious. Why? Because hydrogen gas is explosive. Okay, so explosive. And we generally frown upon explosions in the lab. All right, so you do have to be very careful with it. Now, in terms of the stereoselectivity of hydrogenation, the hydrogen atoms are added in a syn fashion. So they're added to the same face of the double bond. We say the reaction is stereospecific. We only get syn addition, which is meaning, again, that both hydrogens are added to the same face of the molecule. So if we take a look at this unsymmetrical alkene here, so we'd call this 1-ethyl 2-methyl cyclohexene. We treat this with hydrogen and platinum. Again, this metal could have been palladium or nickel. It doesn't matter. We don't discriminate. But you see here that we form two chiral centers that are highlighted in green. Now, with respect to those two chiral centers, what you have to be aware of is that both of the hydrogens are added to the same face of the molecule. That's what the syn addition means. We'll put here both hydrogens on same face, okay, of the molecule. So that would mean that both hydrogens could be going down as they are in this structure here. Now they're left out. I'm penciling them in because I'm your instructor, but we leave them out. Why? Because this is a bond line structure. Or they could both be wedges, as is shown here. And what's the relationship between this pair of compounds here? The pair of compounds here are enantiomers. These are enantiomers of each other. And these are the only stereoisomers that you're going to observe. So if you had written down, and don't write this down because it's wrong, but if you had written down, well, I'm going to get one going down and then the other one coming up, it's not going to happen, okay? We get no anti-addition, only syn addition, so both hydrogens are added to the same face of the molecule. Now, if you're wondering why is that, well, it's because of the way that the hydrogen attaches itself to the metal catalyst. And if you take a look at this here, it says, can you do a hydrogenation without a catalyst? Yes, I suppose you can. However, the activation energy is so high, you see that it's just sky high here, that it's just too slow to be practical or of any kind of use to us as chemists. And so what happens is that when we use a catalyst, not only does it lower the activation energy, but you can see it also changes the pathway. So it has an alternate pathway when we do the catalyzed hydrogenation of a double bond. Now, with respect to the mechanism is not covered in detail in this class. However, this is kind of what the mechanism is here, okay? So you're just going to have to kind of bear with me here. But this, all these black spheres down here, this is the surface of your metal, okay? This is your metal. What were the three options? It could be palladium, platinum, or nickel, any one of those, okay? And what happens is when you subject the metal to hydrogen gas, the H2 molecules break apart and the hydrogen atoms, you see them all here, they kind of look like little lollipops or something, they're like flowers growing out of the top of the metal. They attach themselves to the metal, but you see how they're all in the face of the metal. And so what happens is that the alkene, right, here's your alkene, it kind of comes down, right, just like a UFO or something, right? It just kind of, right? It comes down like that, and it makes that sound too. Anyhow, you see how it comes down towards the surface of the metal, and so the hydrogen atoms are only going to be exposed to one face of that alkene, and so they're going to affix themselves to that one side. So the hydrogen bonds, or the bonds between the hydrogen and the catalyst, break, and the hydrogens attach themselves to the molecule, and so they are added to the same face of the alkene, and we call that syn addition. Okay, so we only get syn addition. I'm not going to ask you to write me an essay about this or anything, or draw curved arrows for that. You see, there are none on here. However, you should have a bit of an idea of how this works, because like I always say, the more that you understand a concept, the easier it is to remember it. Okay, so that is what we're interested in our class, is taking an alkene, okay, taking some kind of alkene, right, and treating it with hydrogen gas, which gets absorbed on the surface of our metal, and then we end up with syn addition to end up with our alkane, okay? Now, with respect to the syn addition here, one thing that you have to be on the lookout for are meso compounds, right? You might be tempted to say, well, these are two different compounds, but remember, chapter 5 still applies, and you can see that, yes, this is a chiral center. Yes, this is a chiral center. There's no debating that. However, there is a plane of symmetry in the molecule, and so this is a meso compound, and therefore these two compounds are the same compound, right? I know you're all aware of that, but if you have to go back and review that idea of meso compounds, that's found in chapter 5. Now keep in mind, this is a meso compound. If you're wondering, wasn't that compound you showed me before a meso compound? No, this is not a meso compound, right? Because here we have an ethyl group and here we have a methyl group. Okay, so it's certainly not a meso compound. So don't get those kind of things mixed up. Now, with respect to heterogeneous catalysts and homogeneous catalysts, you guys have studied chemistry long enough to know what heterogeneous and homogeneous means. A heterogeneous catalyst, those are ones that don't dissolve in the reaction medium. So that would mean platinum, palladium, or nickel. All those metals that I discussed with you, those do not dissolve. They actually stay as a suspension in your reaction medium, whereas a homogeneous catalyst is one that is going to dissolve in the medium. And that's accomplished by using these ligands. So you see we have these organic ligands attached to rhodium here. Now, I am not going to cover homogeneous catalysts with you, okay? So we're going to essentially skip this section, okay, on homogeneous catalysts. All you need to know is the hydrogenation with palladium, platinum, or nickel metal. However, I would recommend reading it, okay? The whole section on asymmetric hydrogenation. Again, you can see here that we are skipping it. However, it might be wise for you to just skim over it quickly. So again, we're going to skip this part on asymmetric hydrogenation. We're going to skip this part on the Knowles hydrogenation. I will not ask you any questions about the Noyori hydrogenation, so you don't have to worry about that. This is the expectation for our class, okay? For Chemistry 3101 at UCCS, these are the kind of questions that we ask. Now, if you're wondering, do I need to know these things for the ACS? The answer is no. They don't test asymmetric hydrogenation in the ACS. So let's take a look here. It says predict the products for each of the following reactions. Now, the first compound, we're taking this alkene and we're subjecting it to hydrogen and nickel. And so we're going to get syn addition. So syn addition. Now let's draw the product that we get once we have syn addition. So let me use a finer tipped pen here. So we have our cyclohexane, okay? And we have our double bond like this, but we're going to have the hydrogen on one face of the molecule, and then here we're also going to have this hydrogen on the same face of the molecule. Do I have to draw those two hydrogens as dashes? And the answer is no, because there's no stereocenters in this compound. Okay, so no stereocenters. So if there's no stereocenters, all I have to do is just say, well, it gets hydrogenated from the alkene to the alkane, and that's totally fine. Okay, nobody would draw it this way. Again, there's nothing wrong with this. Okay, I'm your instructor. I'm just kind of showing you the ropes here. But again, there's no stereocenters in the compound, so you certainly don't have to draw anything with a dash or a wedge if there's no stereocenters. Could anybody tell me, if we do the hydrogenation of this compound, so if we convert this alkene to an alkane, could anybody tell me how many stereocenters would we form once we perform a hydrogenation on this compound? Does anybody have an idea how many stereocenters would be formed when we hydrogenate this compound? So let's take a look here. We would write out the carbon chain like this, okay? If we have one hydrogen going down and then we have the other one going down like this, that would mean that this methyl group is coming up like that, okay? But in this case, there's only one stereocenter, okay? So this is a stereocenter, what I have highlighted in yellow, but this one here is not a stereocenter, right? Because there was already a hydrogen attached there. So that means that there's a hydrogen already there, right? This hydrogen here. And so it's not a stereocenter. And so a more proper way, I would say, to draw that compound would be something along these lines where you manipulate my iPad here, would be to draw this compound and say you're going to get this compound plus it's an enantiomer. So the enantiomer is going to look like this. So these are the two compounds we're going to get, and these compounds are enantiomers of each other. Does that make sense now that I showed you the one stereocenter and why the other one is not a stereocenter? Cha? Okay, cool. All right, awesome. Awesome. You know, the best thing to do is just draw it out. I like to just draw, you know, when you're learning the subject, I think it helps to just draw everything in and say, okay, well, is this a stereocenter? Yes or no? Okay. And then assess it after the fact. I just think it's an easier way to do it. All right. So that covers catalytic hydrogenation. So that covers section 8.9. I just went over the parts that you need to know. Okay. And if you're wondering, you know, will I get to do a hydrogenation in the lab? Well, probably not, again, because hydrogen is a flammable, explosive gas. I can tell you a few stories about doing hydrogenation. It's one of the few times I've been really scared in the lab is I made a little mistake doing a hydrogenation one time. But anyhow, let's move forward. We've covered hydrogenation. So that was section 8.9. We covered hydrogenation. Now in section 8.10, we cover halogenation. And when we're covering halogenation, we're only interested in halogenation with chlorine or bromine, okay? Iodine, we're going to cross that out, and fluorine, we're going to cross that out. If you're wondering why we don't use fluorine or iodine, the reason why is fluorination is too violent, okay? That actually causes explosions, and iodination is too slow, okay? So when we're dealing with halogenation, we're only dealing with chlorine or bromine. And halogenation is kind of in the same vein as hydrogenation because what you're doing is you're taking each carbon of your carbon-carbon double bond and you're adding a halogen to it. So all you need is chlorine or bromine, and in this case, we're using chlorine, so we add a chlorine to each carbon. And this reaction here, okay, is a very important reaction for us on this planet. Why? Because from crude oil, we can get ethylene, and then we treat ethylene with chlorine, and then we can make vinyl chloride. And what do we use vinyl chloride for? We can make polyvinyl chloride, right? And you know that polyvinyl chloride has many, many uses for us in our everyday lives. So let's see, polyvinyl chloride showed up in your organic chemistry class. So when somebody says, oh, this food is good for you, it's organic, you can just say, well, so is polyvinyl chloride. So maybe I should go chew on some of that. Anyhow, so halogenation, again, is only practical with chlorine or bromine. Halogenation with iodine, too slow. Halogenation with fluorine, too violent. Okay, and again, we generally speaking frown upon explosions in the lab. So if you were to take this compound here, so this is just some plain old cyclopentene, okay? If you took some cyclopentene and treat it with bromine, you end up with the trans 1,2-dibromocyclopentanes. However, what's the relationship between those two compounds? Could anybody tell me? And again, this is channeling your inner chapter 5. Could anybody tell me the relationship between these two compounds? They are stereoisomers for sure. What would they be? The wedge is flipped to a dash and the dash is flipped to a wedge. Thanks, Jenny. Exactly. These two compounds are enantiomers. So in this case, we ended up with a pair of enantiomers. And you notice that in terms of stereoselectivity, we only get the products from anti-addition. That means that each bromine is added to the opposite face of the molecule. So one bromine is added to one face of the molecule. So you see one is going up and the other one is going down. Now, something that we don't discuss in gross and dirty detail in this class is, you know, when we go over mechanisms, okay, things like SN1 and SN2, you know, like what's the proof of a mechanism? How do we prove mechanisms? You can't actually watch the electrons move around and things like that. Well, it's a deep subject, you know, studying, you know, how we know mechanisms. However, in section 8.10, the author of the textbook tries to provide you with a little bit of information about the mechanism of bromination or chlorination. And he tries to give you a rationale as to why anti-addition occurs. How do we know a little bit about the mechanism? Okay, because this is one of the important mechanisms for you to know in this class is the mechanism of bromination. Okay, so where he starts out was kind of with a little story. Okay, is he says, bromine, Br2, is a big old molecule. This is it shown here. bromine is such a big atom that bromine, meaning molecular bromine, Br2, is polarizable. Okay, it's nonpolar, but it is polarizable. And what does polarizable mean? Again, it means it's able to distort its electron cloud. So if you have a nucleophile, like in a double bond can be a nucleophile, you see a double bond behaving as a nucleophile here. If a nucleophile approaches your Br2 molecule, and again, this is nothing more than an electrostatic potential map of a bromine molecule is what's being shown here in this pretty diagram, okay? But you see that when the nucleophile approaches, what's going to happen is if the nucleophile is negative, it's going to repel the electrons, okay, that are in the Br2 molecule. And so one side is going to end up delta plus or partially positive, whereas the other side is going to end up partially negative, okay, because again, it's polarizable. So what that means is you could get a nucleophilic attack. Is bromide a good leaving group? Well, heck yeah, it's the conjugate base of HBr, which is a really strong acid. And so you might be tempted to draw this mechanism. However, this is wrong. Okay, this is not the right mechanism. Now, why can I say that? The reason why is because if this was the mechanism, which it isn't, okay, this is incorrect. He's trying to prove a point here. This carbocation is sp2 hybridized, and it is trigonal what? Trigonal planar. If it's trigonal planar, if you form that carbocation, that means that the bromide ion could attack from the top face of the molecule, or it could attack from the bottom face of the molecule. And that way we would get a mixture of syn addition and anti-addition. But we said we didn't see any syn addition, none. We only saw anti-addition. So since we only see anti-addition, this mechanism, what is shown here, is wrong. Okay, this has got to be incorrect. So we'll write here, cannot be correct. Okay, you see the word inconsistent. Okay, it's not consistent with the true carbocation intermediate. Why? Because we don't get syn addition. Here it's showing adding to both faces of the molecule, but we know that this does not happen. And so what does that tell us about the mechanism? Okay, what it reveals is that, number one, this is not the correct mechanism, and that in order to make the mechanism correct, we need another curved arrow. Okay, and we need a different intermediate. And so I expect you to know this mechanism right here. Okay, this first step is actually not two curved arrows. You see your nucleophilic attack and your loss of leaving group, but there's another curved arrow here, okay, which forms a bromonium ion. So this is three curved arrows, okay? You form this thing here that's called a bromonium ion. So you see it's tricyclic, right? 1, 2, 3 atoms in a ring, and there's a positive charge on the bromine. So that's kind of interesting. But if I form that three-membered ring, that means that when my bromide ion comes in and attacks as a nucleophile, that it's going to attack from the least hindered face of the molecule. So you see here, let me use my pen here. I'll write down here, less hindered face. So this explains why we only see the anti-product. We don't see any of the syn addition product. And if you're wondering, hey, isn't this similar to the mercurinium ion that I showed you earlier on, just a couple days ago, which looked something, let's see if I can sketch it out here. It looks something like this, where you have the mercury like this, and then you have the acetate like that. Yeah, it's kind of similar to that in a way, okay? One face of the molecule is hindered like that. So there you go. So here is the total mechanism here. So this is the entire thing, okay? If you want just one, you have the mechanism, the whole thing in one spot, here it is, okay? So the first step is nucleophilic attack, right? Loss of leaving group, and then we also have this curved arrow here to form the bromonium ion. You could call that another nucleophilic attack, kind of. But anyhow, you form the bromonium ion, the bromide comes in and it attacks from the less hindered face, and you end up only with the anti-addition product, okay? Plus it's an enantiomer. And that's it. So there you go. So that is the mechanism of bromination. Chlorination would be the exact same thing. All you would do is change all the bromines for chlorines. Now, where this can get interesting, and I'm using the word interesting instead of tricky because I think interesting is a better word, is since halogenation is stereospecific, meaning we only get anti-addition only, okay, you got to be very careful about the type of alkene that you start with. So if you start with a cis alkene like this one here, you would end up with a pair of enantiomers, right? These two compounds are enantiomers. But if you have trans, look at this. This compound here, okay, this one, you might be tempted to say, I'll draw that plus I'll draw its enantiomer. But remember, if you rotate this bond, it actually shows you that this is a meso compound, okay? So there's no other stereoisomer that you would form in this case. And if you're wondering, would you ask something like this? The textbook is hooked on asking these kinds of things. And later on, we're going to look at syn dihydroxylation and anti-dihydroxylation. And then he loves to mix them up with both of these kinds of situations, okay? So yes, you do have to be very much aware of this, but let's try some practice first and see if we can figure something out here, okay? So we're starting it with this compound here. This would be what? 1,2-dimethylcyclopentene. And we're treating it with bromine. So we're going to get anti-addition. So we could put here anti-addition. So that means that one bromine is going to be pointing up, one bromine is going to be pointing down. So let's start with drawing our ring. Just going to look something like this. Okay, so we'll draw one bromine pointing up. We'll draw the other bromine pointing down like this. And so the methyls are going to have to take the other position. So this methyl will be pointing up, and this one is going to be pointing down like that. Okay, so we're going to get this compound plus one other compound. Could anybody describe that other compound for me? And it's not a trick question or anything. But what would you call the other compound? We've seen it a couple times today. Thanks, Hannah. Yeah, plus it's an enantiomer. Okay, so we would get that compound plus it's an enantiomer. Let's try the next one. Okay, so if we take a look at this compound, we do our bromination. So I'll just write the answer down here. So we start with our skeleton, which is going to look like this. So we're going to have one bromine going up here. The other one's going to be going down like this. So that means the methyl group is going to be pointing up like this. And then we're also going to get its enantiomer in this case. So I'll just draw it this time. Okay, which is going to look something like this. So now this bromine is going to be pointing down. And this one is going to be pointing up. There's my bromine. And now my methyl group is going to be going down like that. Not my best dashes today, huh? But anyhow, you get the idea. So again, this would be a pair of enantiomers. Okay, and make sure you're able to draw the mechanism. Okay, it's very important that you're able to draw the mechanism of this reaction. Again, the mechanism kind of reveals everything to you. So far we've covered section 8.9, which dealt with hydrogenation. Then in section 8.8 was hydrogenation. Then 8.9 dealt with halogenation, so chlorine, Cl2 or Br2. We talked about the bromonium ion. If it was chlorine, it would be a chloronium ion. And now in section 8.10, it's kind of an extension of the chlorination and the bromination. So it's where you take chlorine and bromine, okay, but you have them in water, in H2O as your solvent, okay? When we do a bromination, like these reactions here, or a chlorination, the solvent is not water, okay? So I would never usually write this, but anyhow, it's not water. It's going to be some kind of solvent like dichloromethane or something like that. Anyhow, but the bottom line is if we do a halogenation, meaning a chlorination or a bromination, our solvent is not water. But if you try the reaction in water, okay, you end up forming what's called a halohydrin, okay? So a halohydrin, as I showed you when we started the lecture today, that's when you have a hydroxyl on one carbon and then your halogen on the neighboring carbon. Okay, that's a halohydrin. Anyhow, so we'll just say something like that. So a halohydrin, where do you get a halohydrin? When you do a halogenation in water. Okay, that's how you form a halohydrin. Now, why would that happen? Okay, the reason why is because when you form your bromonium ion, or again your chloronium ion, it doesn't matter. If you do the reaction in water, if water is your solvent, well, what's going to be present in a greater amount? Is it going to be the bromide ion? Is it going to be the bromide ion or water? If you're in water, well, if water is the solvent is present in a much greater quantity. And so water is a nucleophile. It's not a strong nucleophile, but if you put it in the presence of a really powerful or strong electrophile like the bromonium ion, which has a positive charge on it, the probability states that the water is going to more preferentially act as a nucleophile. Could some bromide ions be kicking around and do the nucleophile? Oh yeah, that can happen, but it's mostly going to be water that's going to act as a nucleophile, and so you're going to end up with this kind of intermediate. Now again, it's going to proceed with anti. You're going to get anti-addition. Why? Because the water is going to attack the less hindered face. Now, if you're looking at this and going, well, that's got a positive charge, I don't like that. Well, what's going to happen is another molecule of water is going to come in and do a proton transfer that you see here. So that you end up with your halohydrin. If you do it with chlorine, again, it's called a chlorohydrin. So you end up with the anti-addition product plus it's an enantiomer. Okay. Now, again, this is an important mechanism for you to know. Okay. First of all, we already talked about the formation of the bromonium ion in section 8.9. Okay. And then if you form a halohydrin, what happens is the water is going to come in and attack, not the bromide. Again, it even says here on the slide, can the bromide attack? Yes, but there's going to be so few bromides compared to water molecules that just statistically you're going to have way more nucleophilic attack by water molecules. Now, we've covered the stereo selectivity here, that we get anti-addition. So anti-addition. I think you all follow me on that. However, what would happen if I had an unsymmetrical alkene, right? What would happen if you had a methyl group here, okay? Well, it's kind of interesting that what happens is if you have an unsymmetrical alkene, the regioselectivity is this, that the halide, meaning chlorine and bromine, goes to the less substituted carbon, and the hydroxyl group goes to the more substituted carbon. Now, I've taught this class long enough to know that a lot of students memorize this, okay? Memorize this. However, the textbook does provide us with a rationale. If you're thinking, now this, I had a student raise their hand, before I even get to the next slide and said, Mr. Dion, that makes no sense, because if you form the bromonium ion like this, okay, like that, why in the heck would the water attack here? Because then it's attacking the more hindered carbon, right? And the person said, like, that makes no sense whatsoever. And I said, well, maybe at first glance, if you think about it in terms of sterics, okay? But we don't always think of everything in chemistry, in organic chemistry, to do with sterics. Sometimes electronics play a bigger role. And electronics means positive charges and negative charges. So let's think about electronics. It says here the regioselectivity results from the water attacking the more substituted carbon faster than it attacks the less substituted one. So here you see we have the two methyl groups here, and that is where the water attacks. Why in the heck would this happen? Well, again, it doesn't have anything to do with sterics. It's an electronic effect. The reason why is because the more substituted carbon, when you pass through the transition state, I'm never going to ask you to draw this transition state, okay? And again, most students just kind of memorize this, and that's totally fine. But if you investigate the transition state, look at this. If the nucleophile, meaning the water, attacks the more substituted carbon, that means the positive charge is going to pass from the bromine down to the oxygen, and at some point the positive charge is going to be on that carbon. The carbon that I have drawn here in red is tertiary. It's attached to 1, 2, 3 carbons. It's going to be more comfortable bearing that positive charge than the carbon in blue, which is only attached to 1 carbon. Okay, so that's the rationale. Again, it has nothing to do with sterics. It's an electronic effect. So sterics, again, don't always dominate everything that we deal with in organic chemistry. So with question 8.25, let me show you a couple of ways of solving this problem. Okay, I've taught the class a long time. I've taught it long enough to know that if the question just asks a student to give me the major product that you're going to get when you treat this molecule with bromine in water, what the student is going to say is they're going to get anti-addition, and the OH group is going to be at the more substituted carbon. So if it means the hydroxyl group is going to end up here, and the bromine, right, the bromine is going to end up at this carbon here. That's totally fine, man. There's nothing wrong with thinking of it that way. So my students usually just do this, is they say, okay, I'll draw the skeleton like this. At this carbon here, I'm going to have the bromine coming out. I'm going to have the hydroxyl going in like this. So that means my ethyl group is coming out. And you're also going to get the enantiomer So they're going to write plus an enantiomer. Again, I've asked this question on quizzes many times. I watch my students write their quizzes, and they always do it this way, and there's nothing wrong with it. It's perfect. Okay, it's the right answer. If anybody writes this down, I will give them a big old 100% on that answer. However, something you can try is to think about the rationale. You could say, okay, well, let's see here. What's my intermediate going to look like? My intermediate is going to look like this, where I'm going to form the bromonium ion, which is going to be on one face of the molecule. Come on, iPad, don't do this to me now. There we go. So I'm going to end up with the bromonium ion like this, okay? And then my water, which is my nucleophile, is going to come in, and it's going to attack the more substituted carbon like that. And so then after the proton transfer, I'm going to end up with this compound, okay? Again, I've taught the class long enough to know that usually my students just do this and they nail it, okay? But, every once in a while I'll have students who they just need to know a mechanism for everything, or as much as they can. And if that helps, then that's really great, okay? Give me a thumbs up if you're with me on the stereoselectivity and the regioselectivity of the halohydrin formation. Cha? Okay? Okay, so just to kind of straighten things out in your brain, okay? So we talked about with H2, that's hydrogenation. When we have Cl2 or Br2, that's halogenation. If you use something like HBr or HCl that we've already looked at for a Markovnikov addition, that's called hydrohalogenation. So hydrohalogenation. And if you do a halogenation, meaning chlorine or bromine in H2O, that's called halohydrin formation. Okay, so just to kind of sort those out in your brain, I remember being a student going like, which one's halohydrin, which one's hydrohalogen, and get them mixed up a little bit. And, most of my students just kind of remember what the reactions are. But if you want to get the names straightened out, these are the proper names that we have for these reactions. Okay, just kind of sort things out. All right, so now we're going to turn our attention to what's called dihydroxylation. Okay, dihydroxylation. You guys know what ethylene glycol is used, what ethylene glycol is? Does anybody know where you would find ethylene glycol in your everyday life? Does anybody have an idea? It's something that we probably all use every day. Oh, okay. It's automobile antifreeze. So it's found in antifreeze anyway. It's the major component. There's also propylene glycol in there, but it's antifreeze. Okay, so it can be also used to poison a loved one. So if there's somebody you love and you want to poison them, I'm kidding. Anyhow, but ethylene glycol antifreeze. It has. If you've ever seen the forensic files back in the day, people did poison people using antifreeze because antifreeze has a good taste. It tastes good. Okay, it's got a sweet taste. However, it's a poison, so it tastes good, but it's poison. So, but don't think about using it now because they've put bittering agents in it. So because children and pets had gotten into ethylene glycol before. But anyhow, so a little history on antifreeze here, ethylene glycol. But ethylene glycol is what we call a diol. Okay, so it's a diol. Well, you can guess why, because it's got one alcohol, two alcohols. The prefix di is two, so that's why we call it a diol. And so the process of making a diol, it's got a really tatsy name. It's called dihydroxylation. Okay, so dihydroxylation is forming a diol. And when you see the word glycol usually means that you've got two alcohols in the same compound, so a glycol. Anyhow, the only one we ever look at in this class is ethylene glycol or propylene glycol, but that's for another day. Anyhow, so we're going to look at two types of dihydroxylation. This is always murder when I rifle through my slides, but I got to show you guys, okay? You all showed up to class. So look, there's two types of hydroxylation or dihydroxylation that we look at in this class. We look at syn dihydroxylation, where both hydroxyls are on the same face of the molecule, and we look at anti-dihydroxylation, where the two hydroxyls are on the opposite faces of the molecule. And they're very different, okay? They're two very different things. So you're going to have to bear with me as we go through these. So where the heck was I? It was somewhere. No, it was way over here somewhere. Come on, Mr. Dion. Get with the program. There we go. So anti-dihydroxylation, it turns out, is a two-step process, okay? The first step is to treat it with RCO3H. This thing here, so RCO3H is called a peroxy acid. Peroxy acid, okay? And there's two peroxy acids that we look at. I'm going to show them to you on the next slide. Well, you know what this is. This is just aqueous acid. So in the first step, when you treat your alkene with a peroxy acid, you form what's called an epoxide. So this is a new functional group for today. Believe me, my friend, you need to know what an epoxide is. Okay, so if you have a three-membered ring that's an ether, that's called an epoxide. So if you have something like this is an epoxide. Okay, they're also sometimes called oxiranes. Oxiranes. So if you, every once in a while I have a student who looks up everything I say on the internet, and they'll say, well, I'd say call it an oxirane. You know, what's the right word? Both are fine. Okay, we can call it an epoxide or an oxirane, and we actually study these in detail in chapter, oh good gravy, I think it's chapter 13 maybe of organic chemistry 2. But anyhow, once you take the epoxide and you treat it with aqueous acid, you end up with a transdiol. And so the transdiol comes from anti-dihydroxylation. So the mechanism you see here for the conversion of the alkene to the epoxide, I'll just write down here, will not ask, but is that cool or what? Okay, you have 4 curved arrows all at the same time, and you can see the Lewis structure of your peroxy acid is this. It's like a carboxylic acid, but you stick an extra oxygen in there. And there's 2 peroxy acids that we are interested in Chemistry 3101. One is peroxyacetic acid that you see here. So if you take acetic acid and you put an extra oxygen in it, that's peroxyacetic acid. And the next one is this one here. Well, look at this big old name, metachloroperoxybenzoic acid. The acronym that we use for this is MCPBA. Okay, this is, again, I've taught the class many times. It's usually what my students will write. So if my students want me to know that they're doing anti-dihydroxylation, they'll say step 1, MCPBA, and in step 2, they'll put, come on, you can be neater than that. In step 2, they'll put aqueous acid, okay? Some people always write RCO3H. They're both perfectly fine, but it's the peroxy acid that makes the epoxide. You can see you liberate the carboxylic acid, and then you crack that open with your aqueous acid. That's going to give you the transdiol. So one hydroxyl is going to be pointing up, the other one's going to be pointing down, and in this case you would end up with the enantiomer. Now I told you you do not have to know this mechanism, but if you're a student, and I know you all are, I told you that you do have to know this mechanism. So once you have the epoxide, you treat that with your aqueous acid. So it's going to do a proton transfer to make an oxonium ion. Now you have a positive charge in here, so that makes these carbons very susceptible to nucleophilic attack. So even though water isn't a strong nucleophile, it's certainly strong enough to attack that protonated epoxide. It's going to attack from the least hindered phase, so I'll put here less hindered phase, okay? And then you do a proton transfer with water in the end to regenerate your acid catalyst, and you end up with the transdiol, right? Plus it's an enantiomer in this case. So again, you do have to know the mechanism of this step, step 2. So let's review. Step 1 was MCPBA, or if you want to write RCO3H, that's totally fine. And in step 2, you treat the epoxide with aqueous acid. And this one, you do have to know the mechanism of that particular step, and that is shown on this slide. So again, I know you're all very astute, and you probably noticed, you're like, hey, the last class there was a mercurinium ion, then you showed me what a bromonium ion, and now you're showing me this protonated epoxide, and there's a similarity between all 3 of these intermediates, okay? They all have a +1 formal charge. Well, that's pretty obvious. They all have a 3-membered ring in them. And what I think is most important is that all 3 of these give what? They all give anti-products. Why? Because the nucleophile is always going to attack from the opposite side of the leaving group, or it says side opposite the leaving group, or as I call it, the less hindered face. Okay, there's more room to attack, so that's where it goes. So there you go. You know, one of the things about being a scientist, and I know all of you are interested in science, you know, whether it's organic chemistry, general chemistry, biology, biochemistry, cell bio, whatever, even physics, you know, math, okay? You know, we all come from diverse backgrounds, but one thing that I think that most science students have in common is we all look for, you know, we all look for patterns, you know, and similarities and things like that. And so, you know, you see a pattern here and you notice, okay, I have a 3-membered ring in all of these intermediates. And what do they all have in common? Well, they all give me anti-products. And that's kind of a way you can start to organize all this information in your head, is to look for patterns like that. So what we're going to do in this question is, it says just predict the products that you're going to get if you treat, sorry, you guys, I'm going to silence my phone. When you treat the following alkenes with a peroxy acid followed by an aqueous acid. So we're going to put here step 1. Now, step 1 is RCO3H. If you don't like that, if you said, I want to write MCPBA, that's totally fine. So normally my students just write the answer for the whole thing. They would just write the trans diol plus an enantiomer, and that's totally fine. So if you've already done this one and you're like, Mr. Dion, I'm so far ahead of you, man. Like, I wrote this, okay. I gave the trans diol, I put the 2 methyl groups in the right places like this, and then I wrote plus an enantiomer. Again, I give you 100%, I applaud you. That's perfect, okay? But if it helps you to draw the intermediate, okay, there's nothing wrong with it. So let's do it. Okay, so if we just draw a quick intermediate here, try some of my artistry here. So here's our epoxide that we're going to get. It's going to look like this. Okay, and again, that's the intermediate after the first step. And then you say, okay, after that, I'm going to treat that with aqueous acid, and it's going to give me the trans diol. That's totally fine. It's beautiful. Okay, nothing wrong with that. If you want to practice the mechanism, you could do that too. Like, he just won't stop. Okay, so look, if you, well, I'm kind of running out of space here. So let's write H3O plus here, but let's practice the mechanism once. Let's say we took this compound and we'll just put it down here, and we'll give the mechanism the old college try here. So if I put the hydronium ion, which I know you can draw in your sleep by now, we'll put in our lone pairs. Friends don't let friends leave lone pairs out, right? So we'll protonate, come on, Mr. Dion. We'll protonate the epoxide like this. So we're going to end up with the protonated epoxide. So let me just reproduce this. There's our protonated epoxide like that. And so now water is going to come in as our nucleophile. So water is our nucleophile. It's going to come in. There's no discrimination here between the two faces. So we get our nucleophilic attack, loss of leaving group, and we would end up with, just going to copy and paste this just to make my life a little easier. We would end up with this, where now we have this oxygen with 2 hydrogens attached to it like this. So to get from here to here, what do we have to do? We have to take water and we're going to deprotonate like this, and there you go. So there's a little bit of the mechanism like that. All right, so let's move on. Let's try the, oops, my students go. There you are. Okay, let's try the next one. So the next one, again, we'll just solve it the way students usually do, is they'll write MCPBA, and in step 2, they'll put the hydronium. Again, regioselectivity isn't important here because you're adding 2 hydroxyls. So we'll put this together like this. So we'll have a hydroxyl going down. We'll have another one coming up like this. Of course, the methyl group's going to have to be coming up, and then we'll write plus the enantiomer like that. So there you go. That covers anti-dihydroxylation. Okay. Give me a thumbs up if you're with me on the anti-dihydroxylation. So it passes through an epoxide. Yep. And then you crack that open. with aqueous acid. And again, you only need to know the mechanism for the second part. All right. So now that we've got that straightened out, let's take a look at syn dihydroxylation. And the reason I know we've been going on for quite a while here, but the reason I feel comfortable adding this part in is because even though there's some curved arrows in this section, I'll even write it here and post it to the internet so you can, wave it in my face, is that for syn dihydroxylation, I don't ask any mechanisms. No mechanisms for this section, okay? Now, there are some included. Like I said, this mechanism is included here. However, you don't have to draw any mechanisms for syn dihydroxylation. So if you're looking at this and go, what the heck is that? OS. Oh, yeah, that's osmium. I haven't even thought of that in a long time. It's an element that doesn't come up a whole lot in chemistry class, does it? I don't even know when I would have brought up osmium outside of this class. Maybe if you're looking at an electron configuration or something in general chemistry. But osmium, it turns out osmium is actually a very toxic element, okay? So let me write this down here. Osmium is very, very toxic. I mean, so toxic that when you work with it, you'd want to wear goggles, a face shield, a lab coat, 2 pairs of gloves. You would want a double glove. I mean, osmium is really nasty, but it can be used to make a syn diol, so do a syn dihydroxylation. So the first step that you see here is you take your alkene and you treat it with this thing here. This is OSO4. So OSO4. This is called osmium tetroxide, tetroxide, I guess, like that. Yeah, osmium tetroxide. And yeah, osmium tetroxide, like I said, really nasty compound to work with. But you can see how it reacts and forms this cyclic osmate ester. And since it's a concerted mechanism, right, this is concerted, meaning all arrows are done at the concerted, okay? Means all arrows occur at the same time. So that means that the osmium tetroxide adds in a syn fashion, okay? So then what you do is, who remembers this here, Na2SO3? So this goes right back to your general chemistry days. So this would be sodium sulfite, okay? Sodium sulfate. And this one here would be sodium bisulfite, NaHSO3. So sodium sulfite and sodium bisulfite. So you take your cyclic osmate ester and you treat it with sodium sulfite in water or sodium bisulfite in water. So what does this look like if you were to write it down? There's 2 possibilities. Step 1, OSO4. Step 2 would be sodium sulfite in water. So we just write in water. So just write a /H2O so everybody knows it's aqueous. Or you can write OSO4 and sodium bisulfite for your second step. So sodium bisulfite in water. Okay, so it just means the sodium bisulfite or the sodium sulfite is dissolved in water. That's all that means. Okay. The problem with these 2 reactions, okay, and I'm the one who taught them to you, so it's totally fair game for the class. You can use those anytime you want, my friends. The problem with these reactions, though, is that the amount of osmium is stoichiometric, meaning if you have 1 mole of your alkene, you would need 1 mole of osmium tetroxide. And like I said, osmium is so toxic that using it in a stoichiometric amount is really crummy, okay? And people don't want to do that. I even worked with somebody one time, I mean, this is years ago, and the person actually said, they were asked by our supervisor, said, could you do this reaction using osmium? And the person literally said, no, I refuse to. I'm not doing it, okay? And so they had to find somebody else to do it. So again, osmium tetroxide, expensive, toxic. And so luckily, chemists have found a workaround that instead of using a stoichiometric amount of osmium tetroxide, what we use is a catalytic amount. So if it's catalytic, I mean, I've used osmium and I've gotten away with just using 1 drop. So 1 drop is all you need when it's a catalyst. Why? Because the catalyst gets recycled over and over. But in order for it to be recycled, you need what's called a co-oxidant, which regenerates the osmium tetroxide. This mechanism is not covered in the textbook whatsoever, but there's 2 possibilities for your co-oxidant. You can use NMO, and NMO stands for N what is N-methyl morpholine N-oxide. Now, an N-oxide is a functional group that we don't study in detail at all in our class, but because if you're like, well, what the heck is that? Well, it's got a positive and a negative charge in the same functional group, so they neutralize each other, but that's called an N-oxide. And again, it's a functional group we don't study in detail, so don't stress about drawing NMO. Usually what my students will write is they'll just write OSO4 catalytic. So they just put catalytic like that, and then they'll put NMO. NMO as the co-oxidant, like that. Okay. Now the other option beside using NMO is to use an alkyl peroxide. This one here is tert-butyl hydroperoxide. Okay, and that's also used as a co-oxidant. I don't know if it's the solutions manual or what, because I don't really look at the solutions manual a whole lot. But my students never use tert-butyl hydroperoxide. They always whip out the NMO, so I guess it's the one he probably uses the most. And it's the one I've used when I did this reaction before. So there is another option, okay, for syn dihydroxylation. So far, let's keep track, okay? We've covered this one, so that's our first one. This is our second one. These are all doing the same thing. This is our third one, is using OSO4 in a catalytic amount with NMO. This is our fourth one here. So that's 4. And then he teaches you a 5th way of doing it, okay? Another way of doing it is using potassium permanganate. So the conditions are this. I'll write them down for you. So it's KMnO4, which is potassium permanganate. You guys remember the permanganate ion in sodium hydroxide. And then we keep that at a cold temperature. Now, this is a perfectly legitimate way of making a syn-diol, it's syn dihydroxylation. However, the problem with that here is it tells you that the synthetic utility of potassium permanganate is limited. Why? Because it reacts with everything. Okay, so if you have any other functional groups in your compound, KMnO4 is going to oxidize it. So it's not the best choice, but it is presented in the textbook. And so if you choose to use that in an exam, let's say you're taking, chemistry 3111 with me in the fall, and you whip that out on a quiz and say, well, this is what I would do to make a syn-diol. It's perfectly fine. Okay, I will accept it, no problem. But there you go. That's a total of 5 different ways that the textbook teaches you how to make a syn-diol. Okay, a lot of different ways to make a syn-diol. So what we're going to do now is we're going to take a short break, and then we'll come back and we'll solve these problems. Okay, and each one of them you make a syn-diol, but you have to make a judgment call in all of these as to whether you make a stereocenter or not. And maybe you even make a meso compound in one of these. So you have to figure that out as well, okay? So we'll take a short break, and then we're going to come back and we're going to solve this problem. And after that, we're going to look at I promise, this is the very last reaction, okay? Last one, okay, in the entire chapter is the oxidative cleavage reaction, which we sometimes call ozonolysis, okay? Because it's the only type of oxidative cleavage that we look at in this class. But we're going to start with this one when we come back from our break.